Welcome to the deep dive. Today, we're setting our sights on modern computing security. We'll start high level, but then really drill down. We're talking infrastructure protection, securing everything from deep in the data center right out to those specialized IoT devices on the edge. We've got a stack of pretty rigorous research here today. It gets a really comprehensive look at the tools, the tactics, the threats involved in protecting hosts and data, virtual, cloud, embedded the works, our mission to kind of synthesize the crucial differences, like, say, the gap between basic antivirus and advanced XDR. We want to give you a rapid handle on this really complex landscape.
Absolutely. And, well, if we want to get modern infrastructure, we really have to start where so many systems actually live now, inside the box, but not physically. We're talking virtualization. And securing that world, it starts with the hypervisor. That's the critical piece of software or sometimes firmware that lets us run multiple isolated systems all at once.
Okay, and these systems, they have specific names, right? Critical terms we need to know. The host, that's the physical machine, the actual server.
That's it, the metal box in the rack.
Yeah.
And the guest is the virtual machine, the VM, running on that host.
Right, and the crazy part is one host can run, what, dozens of guests? And to the network, they just look like separate computers?
Exactly, dozens, sometimes hundreds. And the business drivers for this are just immense. It really powered the whole cloud revolution. First, you've got cloud elasticity. That's the ability to dynamically change resources, add more CPU, more memory based on the current load, often without even rebooting the guest machine.
Okay.
And second, there's cloud scalability, which is just the capacity to easily add more stuff like disk storage or network bandwidth whenever you need it. These two, elasticity and scalability, they completely shattered the old way of thinking about fixed hardware limits.
Okay, so let's unpack a really core distinction then, because this really dictates the security model, doesn't it? The two types of hypervisors.
Oh, this is absolutely fundamental. You've got Type I, people call the bare metal hypervisor. Yeah, it runs directly on the hardware itself. There's no host operating system underneath it that it needs. Think VMware, ESXi, or Microsoft's Hyper-V.
Okay, so Type I is right on the hardware. So where does the other one, Type II, fit in? That feels more common for, desktop use.
It is. Type 2 runs as a software application inside a regular operating system, like running VirtualBox or VMware Workstation on your Windows or Mac laptop.
Ah, okay.
And the security implication there is massive because Type 2 sits on top of an OS, right? If that underlying OS gets compromised, well, the guest VMs are immediately at risk too.
Right, the foundation is shaky.
Exactly. Type I is inherently more secure. Its attack surface is just much, much smaller because it talks almost directly to the hardware, less underneath it to go wrong.
That makes total sense. Okay, so moving from the architecture to how it's delivered, let's talk VDI, virtual desktop infrastructure.
VDI. Yeah, it's a really brilliant solution, especially for big organizations with lots of users. The actual computing, the processing, it all happens back on the servers in the data center. Only the screen display and your keyboard clicks get sent back and forth to what's usually a pretty cheap, simple, thin client device on the user's desk.
So management gets way easier.
Dramatically easier. Updates, re-imaging, deploying new desktops, it's all centralized. But when you talk about the virtual desktop environment, VDE, you have to think about persistence.
Persistence, meaning whether the user's changes stick around.
Exactly. Is it persistent, where the user keeps their customizations, their files between login sessions? Great for the user experience, sure, but it's harder to maintain, potentially riskier. Or is it non-persistent, where the desktop basically gets wiped clean every time the user logs out?
That sounds way more secure.
It is, significantly. Any malware someone picks up, any weird configuration changes they make, poof, gone when they log off. It resets to a known good state every time.
Okay. And when security teams need, total isolation for testing sketchy files or malware analysis, that's sandboxing.
A sandbox is just an isolated area to run things.
Right.
Often, we use a full VM for that. But you also see lighter tools like crootjail on Linux.
Crootjail.
Yeah, it's a command that basically locks a process or even a whole command shell inside a specific directory.
Sure.
It can't see or affect anything outside that little jail. It's not full virtualization, not isolating hardware, but it's really useful for, say, running an old, maybe insecure application or containing a shell session you think might be compromised without the overhead of spinning up a whole VM.
That's a useful distinction. Process isolation versus full system virtualization. Okay, but let's talk risks. What are the dangers inherent in using virtualization?
Well, the first one is surprisingly simple.
Yeah.
VMs, they're basically just files. Big files, sure, but still files.
Meaning they can be copied, stolen.
Yeah. Copied, moved, exfiltrated, just like any other sensitive document if you don't secure access properly. The second risk, though, is the really scary one, VM escape.
Right, I've heard of this. This is the nightmare scenario.
It is. It's a critical vulnerability, usually in the hypervisor itself, that lets an attacker break out of their isolated guest VM and get access to the underlying host system,
Whoa.
or potentially even jump sideways to attack other guest VMs running on the same host.
That sounds like it completely breaks the whole model. How often does that actually happen?
Thankfully, it's rare in the wild. Successful VM escapes are like the crown jewels for exploit developers, very hard to find and execute. Hypervisor vendors work incredibly hard to prevent them, but organizationally, the much more common and frankly often more costly problem day-to-day is VM sprawl.
Sprawl. That's interesting because it's not really a technical failure, is it? It's more like bad housekeeping.
Exactly. It's the uncontrolled creation of VMs. A developer spins one up for a quick test, then forgets about it. Another team clones one for a project, finishes, but never deletes it. And suddenly you have hundreds, maybe thousands of these forgotten VMs running.
Eating up resources.
Eating resources, creating security holes because nobody's patching them, causing compliance headaches because they're undocumented, hitting performance, and yeah, just costing money and licenses and power.
So how do you stop that?
Policies. Strict VM creation policies, mandatory auditing, actually checking what's running, and clear documentation. Who owns this VM? Why does it exist? When can it be decommissioned?
Right. Discipline. So securing the foundation starts with getting that initial setup right, using master images.
Master images are crucial. They provide that secure, standardized starting point. You build one perfectly hardened, configured workstation or server image with all the standard software, and then you deploy that. It gets rid of the snowflake server problem, where every machine is slightly unique and hard to manage, reduces attack surface, controls costs. It's fundamental.
And once you deploy from that master image, securing the OS itself follows a life cycle, right? First step, establish that initial baseline configuration.
Correct. Lock it down from the start. Then comes step 2, integrity measurements. Regular checks. Vulnerability scans, configuration checks. You're looking for any drift from that secure baseline. Unauthorized file changes. New services popped up. Missing patches.
Got it. And step 3.
Remediation. You find a problem, you fix it. Actively correct those deviations and bring the system back into compliance with the baseline. It's a continuous cycle.
And keeping that secure state requires strong controls. Patch management is obviously huge, but the key thing you mentioned is testing.
Oh, absolutely critical. You must test patches first, preferably in a staging environment that mirrors production as closely as possible.
Because deploying a bad patch could take everything down.
Precisely.
Yeah.
You could cause an outage far worse than the vulnerability you were trying to fix. And speaking of avoiding outages, change management is just as vital. No changes go into production without being proposed, documented, reviewed by stakeholders, and formally approved. It prevents those oops moments that cause unexpected downtime.
Okay, so securing the OS is about baselining, maintaining, controlling change. Let's pivot now to securing the endpoint itself. This feels like it's about controlling what code can even run.
Yeah, that's a big part of it. We have 2 main strategies for application control. First is the older way. Application block lists or blacklisting.
So just listing the known bad stuff.
Exactly. You maintain a list of prohibited applications, maybe known malware, maybe unauthorized tools like P2P software, and you prevent them from being installed or run. Simple, but it's reactive. You have to know it's bad first.
Which leads to the better approach. Application allow lists or whitelisting?
Whitelisting. It completely flips the script. Instead of saying what's not allowed, you define only the software that is authorized and approved to run.
So if it's not on the list,
It doesn't run, period. Doesn't matter if it's brand new 0-day malware or just some game an employee downloaded. If it's not on the approved list, it's blocked. It's a much, much stronger defensive posture against unknown threats.
that strategic shift seems reflected in how endpoint security tools have evolved, too. This is where we see that big jump you mentioned, from basic antivirus, AV, which feels almost quaint now.
Well, it served its purpose for a long time.
Yeah.
AV was primarily about malware prevention.
Yeah.
It worked by checking file signatures against a big database of known viruses and malware. Relatively low complexity, pretty cheap. But its huge weakness was it only knew about known threats. If something new appeared, AV was blind until its database got updated. Purely reactive.
Okay, so the threat landscape got too fast for that. Then came the next big step, Endpoint detection and response, or EDR.
EDR was a major leap. It moved beyond just signatures into detecting both known and unknown
Oh,
threats
yeah.
through real-time monitoring and, crucially, behavior analysis.
So it's not looking for a known bad file, it's looking for suspicious activity.
Exactly. Is this process suddenly trying to encrypt files? Is Word trying to launch PowerShell commands? EDR spots those anomalies, and it has response capabilities built in.
Like what?
It can often automatically isolate a compromised endpoint from the network, stop malicious processes in their tracks, and gather detailed telemetry like a flight recorder for security teams to investigate what happened.
Okay, so EDR is smart, responsive, but focused just on the endpoint itself, which brings us to the current state of the art, XDR, extended detection and response.
XDR takes the EDR concept and broadens the view. It extends that detection and response capability across multiple security layers, not just endpoints, but also networks, cloud environments, email systems, identity systems.
So it connects the dots across the whole organization.
Precisely. It uses advanced analytics, often AI and machine learning, to correlate weak signals from different domains into a high-confidence picture of an attack. It sees the bigger pattern. This allows for a much more coordinated, effective response across the entire IT infrastructure. It's complex, yes, and usually more expensive, but it shifts security from siloed monitoring to truly unified threat intelligence and action.
That's a huge shift in capability. Now, alongside these software defenses, we're seeing security pushed right down into the hardware itself. Let's talk disk encryption. We mostly know FDE, full disk encryption, like BitLocker in Windows, but then there are SEDs, self-encrypting drives.
SEDs are generally the superior technology, especially for performance and key management. They are essentially hardware-based FDE.
Meaning the encryption chip is built into the drive.
Right into the drive controller itself. The encryption key often never leaves the drive hardware. All the encryption and decryption happens right there on the drive at hardware speed. This means minimal performance impact on the main system CPU, unlike software FDE, which uses system resources. And it's generally considered more secure because the crypto operations are self-contained.
Okay. And for ensuring the system hasn't been tampered with before the operating system even boots up. That's where things like the Trusted Platform Module, TPM, come in, and HSMs.
Absolutely essential for modern security. TPMs and their bigger, more robust cousins, hardware security modules, or HSMs, provide what we call a hardware root of trust.
A root of trust.
Yeah, secure anchor point. They enable features like secure boot and boot attestation. Basically, the TPM stores cryptographic measurements like fingerprints or signatures of critical boot files, the firmware, the bootloader, the OS kernel. When the system starts, it checks the current files against those stored signatures. If anything's been modified, maybe by a rootkit trying to embed itself before the OS loads,
The TPM blocks the boot.
blocks it cold, or flags it as untrusted. It prevents boot-level malware from taking hold by verifying the integrity of that crucial startup sequence.
Okay, and this leads to maybe the ultimate hardware protection, securing data while it's actually being used, while it's in memory.
Right. Protecting data in use. That's the job of the secure enclave, or more generally, a trusted execution environment, TE. Think of it like a tiny, highly secure vault inside the main processor.
Inside the CPU.
Yeah. The T creates an isolated region of memory and execution that's completely walled off from the main operating system and other applications. So if an application needs to process something incredibly sensitive, like, say, your fingerprint data for login, or decrypting a master key, that calculation happens inside the enclave.
So even if the main OS is totally compromised by malware.
The malware can't see inside the enclave. The memory and processes running there are invisible and inaccessible from the outside. It protects secrets even when the rest of the system is hostile. Intel SGX is a common example of this.
Wow, okay. So we've covered securing the host, physical and virtual, down to the silicon. Let's shift gears now, move out from the data center into the cloud and the mobile edge, starting with the cloud service models.
Yeah, we have to be clear on who is responsible for what in each model. It's crucial. SaaS, software as a service, is the simplest.
That's like webmail, right?
Yeah.
Google Workspace, Office 365.
Exactly. The vendor manages pretty much everything, the application, the platform, the infrastructure. You just use the software over the internet. Very little security burden on the customer, relatively speaking.
Okay, then you move down the stack into shared responsibility, PaaS, platform as a service.
With PaaS, the vendor provides and manages the underlying platform, the OS, databases, middleware, runtime environments. They keep all that patched and up to date. This also includes newer things like serverless computing. The customer's responsibility is really focused on their own application code that runs on the platform and their data.
So the vendor handles the OS patching, which is a big relief.
Huge. And then the model with the most customer responsibility is IA, infrastructure as a service.
This is like renting raw servers, storage, networking in the cloud.
Pretty much. You get access to the basic hardware building blocks, usually as VMs. The cloud provider secures the physical data center and the underlying hypervisor that runs your VMs. And this is critical. The customer is fully responsible for everything inside that VM, securing the guest operating system, patching it, installing and securing all the application software, managing firewalls for it. It's much closer to managing your own on-premise servers.
Right. The responsibility line shifts significantly. We also hear a lot about multi-cloud. What's the driver there?
Multi-cloud just means using services from 2 or more different cloud service providers, or CSPs. Maybe you run your main apps on AWS, but use Azure for specific AI services, or Google Cloud for data analytics.
Why do that? Seems complex.
Several reasons. Avoiding vendor lock-in is a big one. Risk mitigation, if one provider has an outage, maybe you can fail over some services. Cost optimization, potentially. Or just accessing best-of-breed services from different clouds.
Okay. Now, when you move into the cloud, managing security changes. The scale is different. You mentioned secrets management being vital.
Non-negotiable in the cloud. You have potentially hundreds or thousands of applications, services, scripts, all needing credentials, API keys, passwords, database connection strings, certificates.
And you can't just hard code those into config files.
Absolutely not. That's a recipe for disaster. Secrets management provides a central secure vault to store all these secrets. Applications request them programmatically when needed. They're often rotated automatically, and access is tightly audited. It drastically reduces the risk of credentials leaking out.
And another key cloud security tool is the CASB, Cloud Access Security Broker.
Right. A CASB acts like a security checkpoint or a proxy sitting between your users and your cloud services.
It's a gatekeeper.
Sort of. It enforces security policies as users access cloud apps. It can provide visibility into what cloud services are being used, even once IT doesn't know about shadow IT. Enforce data loss prevention, DLP rules, to stop sensitive data leaving, scan for threats in cloud traffic, and provide granular controls over how services are used. It's essential for governing cloud usage securely.
Okay. And within the cloud architecture itself, we need things like high availability across availability zones, AZs. That's for redundancy.
Yeah, AZs are basically separate data centers within a cloud provider's region. Designing your application to run across multiple AZs means if one data center has a problem, your app keeps running from another. Basic resilience.
And security groups. Are those just cloud firewalls?
Essentially, yes. They act as virtual firewalls for your VMs, controlling inbound and outbound traffic based on rules you define: port numbers, IP addresses, protocols. They're fundamental for network segmentation in the cloud.
And you mentioned infrastructure as code, IAC. That sounds powerful.
It is. IAC means you define and provision your entire cloud infrastructure networks, VMs, load balancers, security groups, everything using code or configuration files. Tools like Terraform or AWS CloudFormation.
So instead of clicking around in a web console,
You write code. This makes deployments repeatable, consistent, version-controlled like software, and auditable. It's key to managing cloud environments at scale securely and efficiently.
Okay, let's move right to the edge now. Mobile devices and IoT. Mobile brings its own set of risks, doesn't it? Different from desktops.
Oh yeah. Big ones include users intentionally bypassing security controls through jailbreaking on iOS or rooting on Android. This gives them admin-level access, letting them install anything, but it also breaks the OS's built-in security model.
And sideloading.
That's installing apps from outside the official app stores. Sometimes necessary for custom enterprise apps, but hugely risky if users just download random stuff from the internet. Also, simple things like messaging basic SMS and MMS are often still sent unencrypted in plain text. That's a risk people forget.
So how do organizations manage this potential chaos? That's mobile device management, MDM.
MDM is the core tool set. It allows organizations to enforce policies and controls on mobile devices, whether they're company-owned or personal devices used for work, BYOD.
What kind of controls?
Essential things like remote wipe. If a device is lost or stolen, you can erase it remotely. Storage segmentation or containerization, creating a secure, encrypted work area on the device, separate from personal apps and data. Also, things like enforcing passcodes, controlling which apps can be installed, configuring VPNs, and even more advanced stuff like geofencing, restricting access based on the device's physical location, or context-aware authentication, which might require stronger proof of identity if the user is connecting from an unusual network or location.
Right. Layering controls based on risk context. Okay, last area. Specialized systems. Embedded devices, IoT. Things like SCADA.
SCADA supervisory control and data acquisition. These are the systems that run critical infrastructure. Power grids, water treatment plants, manufacturing lines, pipelines, industrial control systems, ICS.
The stakes there are incredibly high. A hack isn't just data loss, it could be physical damage, right?
Exactly. Which is why security is paramount and different. These systems often need to be strictly segmented from the main corporate IT network, sometimes using an air gap, a literal physical disconnection from any other network. Keeping them isolated is key.
But the broader IoT world, the smart speakers, cameras, wearables, appliances, that seems like the Wild West. What's the core problem there?
Honestly, security is very often an afterthought. The main drivers for many IoT devices are low cost and speed to market,
So security gets cut.
or just minimal effort is put in. This leads to devices shipping with weak default passwords, unencrypted communication, limited processing power or battery life that makes running proper security software impossible, and update mechanisms that are patchy or non-existent. Patching a million smart light bulbs is difficult. They're often designed to be disposable, not securely maintained for years.
That sounds like a huge distributed vulnerability surface.
It absolutely is.
Well, we have definitely covered a massive amount of ground here. Started right down at the bare metal hypervisor, traced the critical evolution from reactive AV up to that holistic XDR philosophy. We went through hardware roots of trust, TPM, secure enclaves, then out to the complexities of cloud security architecture, and finally landed on this sprawling, often insecure IoT edge.
Yeah, it's a lot, but I think what really stands out looking across all of it is the reliance on layers. You need that hardware root of trust as a foundation. You need strict application control like whitelisting on the endpoint. You need rigorous network segmentation, whether it's in the cloud with security groups or, air-gapping SCADA systems. The big takeaway, I think, for anyone working in security today is that necessary shift in focus, moving away from just reacting to known bad things and towards proactive policies, centralized management, automation, and really enforcing those secure baselines consistently.
Right, proactive, not reactive.